So you just need one lab, sorry. So make sure you just get one lab. The printer had an accident, so you used a bunch of colored paper. So just pick your favorite color, I guess. Yeah, we're out of space. So. Yeah, if you have things to turn in, I can take it now or after class. We've lost the desk here. Also, I would say we have a turn-in pile here, but out of surface area apparently. Take yep. Oh, thank you. Thank you. Oh, thank you. Yeah, I have 1, 2, and then the lab. I have separate. It might have walked away from this room. Oh, here's one actually. Thank you. All right, welcome. So as you come in, you can kind of turn in your stuff, like I said, now, after class. I'm not too picky. I think the official due date on Blackboard is Thursday. So again, right, take an extra day or two to work on your homework, get it correct. So homework answers are posted. And then if you did turn it in, I at least kind of mark a few notations and write things. So you get full points, though, just for attempting it. And I'll try to hand back the assignments. I don't know people's names yet, but I'll try to learn them quickly. And then don't forget the reading questions. So I took a glance at Blackboard, and it looks like a few people have done them. but you don't want those reading questions to sneak up on you. And again, I don't really do late penalties. That's too much for me to keep track of. But you don't want it to be, week 10 and you haven't done a single reading question. So that'd be kind of painful. So don't forget about that. Again, they're in Blackboard, so if you need help navigating to there, let me know. And then happy fall, right? As soon as we get together in fall, everybody starts getting sick already. So people have let me know, and that's fine. So there's a link in Blackboard so you can watch my lecture live. And if you are sick and at home, just say hi in the chat so I know you're there. And I do pay attention to the chat. Otherwise, right, you can watch the recording later by that same link on the YouTube channel. What else should I say? Oh, and then labs. So like I said, you have about a week. I had a lot of people emailing me trying to get to the journal article. For some people, I was like a little, not mean, but I was like, try again, try again. So try your credentials. If they're not working, the library should be able to help you get like a temporary credential or something. Or ask me for help if you forgot how to navigate to the page or it's on the YouTube video. But again, you can turn those in by Thursday. And then if you have the abstract and you can't print it, just email it to me. So people have already been emailing me abstracts. So I'll print them and, find your lab report. Other questions, comments? Anything else come up? All right, so let's keep diving into it. I know we're a little behind on your homework. So like I said, if you need to take more time for chapter 2, that's fine. And so kind of the mind frame that we want to be in is we're both trying to understand what the states of matter are, right? So obviously we want to go over that because that's very basic knowledge. But it's also telling us, okay, well, what state of matter is this? And then what are we going to do to it, right? What are its properties? So that's, again, the mind frame, right? How are we going to separate these compounds? How do we mine out all these different elements that we have? And so again, just to make sure we're all on the same page. So of course, matter can be classified according to its state, solid, liquid, gas. And again, we're mainly focusing on solid, liquid, gas in here, right? I know that plasma exists, but again, that's special cases, and we're not focused on that. And then, right, we also want to note its composition. So we're going to, again, right, work to understand that. What does it mean? What's an element? What's a compound? What's a mixture? What do we see in real life? And then, of course, right, I mentioned it. Yes, we've seen this for water, solid, liquid, gas. But again, you want to change your thinking to kind of think chemically. So when you see a solid object, you're kind of also really envisioning this. And so in our solid matter, and we can either look at our representation. So again, they're tightly packed into place. And so this just means that, right, they can't slide past one another. So there's still molecular motion, so that's what we want to emphasize. So your electrons are still moving around, right? They can still be vibrating, still be some wiggling, but they're not really going anywhere. And so then liquid matter, oh, and then I'll also say fixed volume and fixed shape. So right, again, something is solid, so you can't really manipulate it. So again, that can get into other properties, right? Hardness and other ways to classify our material. And then, so adding energy or heat here. So then, right, again, thinking of water, you start adding heat. Now those molecules can start moving and sliding past one another. And so that's our liquid state. So again, right, they slide past. You can see that it's pourable. And so we still have a fixed volume, right? But now no fixed shape. And again, you've seen that, right? You can pour liquids from one container to the next. They just fill up that container. And again, they're sliding past one another. So we'll work to understand as we go deeper in the course again, what kind of drives these trends, right? Why is something a liquid? So why is water a liquid? Why is pentane a liquid? So getting into those things, we'll look at that as we, again, progress in the course. Sorry. There we go. And so gas, the key word with gas is that gases are compressible. And so you may have seen, right, tanks. For example, right, you have liquid nitrogen. So liquid nitrogen or nitrogen, right, comes in like these giant tanks, and then they have a valve, right, so it comes out at about 230 psi for air. And so again, right, just showing the compressibility of that nature, where you can compress some gases all the way down back to a liquid form, and then again, right, re-expand them at a high pressure. Or if you go lower pressure, this is now too many fun facts, but like about 20 or so psi, that's where you get your liquid coming out. So the same tank can be used for both air and liquid, again, kind of depending on what pressure you have it at. And so gaseous, right, we've added even more energy, and so now they're widely spaced. So again, right, the compressible, so they can fill a whole room, and right, you know that, so if you were to open something volatile like a perfume or something, right, that perfume would make its way throughout the whole room there. And then we'll add, right, no fixed volume and no fixed shape. So again, right, our gas always fills the room there. And then just text with the notes, and then again, right, more examples. So obviously ice, but then we can think of other things that would be on the periodic table, aluminum, any other metals, right? So again, many of our metals, if you look around, especially at the periodic table, you have a bunch of solids. So that one, the one in the back, is black for solids, blue for liquids. So right, very few things in its elemental form are liquids. And then right, we have, of course, a few gases, so the noble gases. And diamond, obviously always a good example of a solid. And again, just examples of liquid to put it in context. So water, alcohol, gasolines. And so, right, this alcohol could both be ethanol that you consume. So now I'll draw out the form. So ethanol, so 2 carbons. Or it could be any other alcohol, right, like isopropyl alcohol. Or any other alcohol. So, and then again, gas, so the idea that it's compressible. And of course, you could come up with examples of gases, so nitrogen, oxygen, CO, CO2. And I'm sure you could give me many more. All right, so again, right, a big part of chemistry is what is it, how do we separate it? And so, right, we have this kind of classification of elements flow chart. And so this just kind of helps us categorize things. So we have, just starting with whatever substance we're looking at, so matter. And then we want to determine, is it one type of particle? And so this is really asking, right, is it an element or compound? And so maybe we first have to answer, well, what is an element or compound? So remind me, where do we find our elements? Yeah, just periodic table, right? So that's always a good place to start. So again, right, I don't expect y'all to know everything, but okay, new substance, is it on the periodic table, right? Good place to check. So periodic table. And then again, right, don't get confused by your allotropes. So allotropes are all considered elements. So again, right, C60, P4, etc. there. So we went over that right previously. And so, oh, right, I read all your wonderful comments and everything. And so a few people said, you know, that they like write slow or I move fast. And especially like I'm trying to move fast in the beginning, right, because there's a lot of background knowledge, kind of making sure we're on the same page with language, but I'm still trying to keep it moving forward since this could be a repeat. But just like slow me down, right? If you're confused, if I'm moving too fast, like do not hesitate, right? That's why you take it in class, right? An in-person class, right? So that you can ask questions, right? I'm not just a video that goes on and on. So yeah, feel free to chime in if I'm moving too fast. And so then kind of the trickier question, kind of especially, right, for new chemists, I'll call you guys. For new chemists is it a compound? So first of all, what is the definition of a compound? Do we remember?
2 or more elements.
So 2 or more elements, so that's good. What else? So fixed proportions, or any other ways to say that? So I'll say 2 or more elements. And then I like that, fixed proportions, but I'll also say it in another way. Defined chemical formula. Right, so it's more than just a ratio. It's saying these things always form in this proportion, right? And that kind of goes back to how they eventually teased out the difference between CO and CO2 and trying to mix things in different ratios, right? And figure out in what proportions could they make CO or CO2. And so this is tricky. So let's look at some examples too that might come up. For example, right, drugs are always a good thing to talk about. And so sometimes this is prescribed. So you may, if you had surgery or anything, or, you know, pain for whatever reason, perhaps you've been prescribed like Norco before, or any other of its common names, brand names. And so Norco, right, is actually a mixture. And so again, this is why I say, like, you might have to look up stuff initially when you're trying to learn. So it's a mixture, right, of hydrocodone and acetaminophen. And now let's look up those 2 substances. So hydrocodone, right, is just an opioid. And so again, define chemical formula. So now we can say, here's our structure for this compound, right? It has a formula. So if we scroll down, there's our formula. So it's always C18H21NO3. And again, right, it's always the structure shown here. And then I just wanted to show, because oxycodone is pretty similar to hydrocodone, so I just wanted to point out that their main difference, so this one has a hydrogen here, and oxy has an OH there, so alcohol group. So they're pretty similar. We won't get into too much. And then, right, acetaminophen. So obviously in the news headlines right now, but again, define chemical formula. There's our defined chemical formula, right? So we can clearly see, okay, yes, these are compounds. So good distinction. So let me put that on our notes there as some examples. So aspirin is another one. So I can't spell. I know I misspelled that. Acetaminophen. So Tylenol. And then hydrocodone, or, right, oxy. So again, both of those, right, distinct chemical formulas. And so now let's try to classify our mixture, right? So we mentioned, oops, sorry, wrong window. So, right, again, we'd mentioned that Norco was then a mixture. So let's look at our class types of mixtures. So then we have to ask ourselves, okay, is this mixture uniform throughout or not? And so you guys can probably answer that. If it's a pill, like, again, Norco or any sort of mixture of a medication, do you think it's going to be heterogeneous or homogeneous? Yeah, homogeneous, right? And at least it better be, otherwise you have serious manufacturing issues. But yes, right, we expect a nice homogeneous mixture, so they get the powders all nice mixed in the correct ratios, right? So again, we don't want to confuse kind of ratios of mixtures for fixed proportions of chemicals, right? Because you could always adjust the ratios. I think for Norco, for example, it's typically given as 5/325. Yeah.
Does that still apply for like time-release capsules or like an enteric coating on a pill? Or is that?
Yeah, I mean, that I would probably classify that as like a mixture. Is that what you're kind of talking about, or?
The homogeneity over heterogeneity.
Yeah, I mean, that one I would start to say that, right, so now this is where things can get trickier if you're trying to explain to me, like, whether you think it's heterogeneous or homogeneous. So, yeah, if you've got some sort of, like, capsule that's separate, so I don't know if you guys have ever, like, tried packing your own pills, or maybe some of you are, like, pharmacists, right? You have this little soluble capsule, and so, yeah, you could say that that is then heterogeneous, right? If you have a separate little capsule and then it has powder in it, right? So kind of two separate substances. So that does get a little tricky. So if that ever comes up on an exam, right, you can write an explanation that, like, yes, the outside capsule material is separate. So it depends, right, whether it's a pressed pill, because I think Norco is more like a pill that they just like press together versus, right, a capsule that you pack with a certain ratio of things. So yeah, good question there. So, right, again, pills can be in different ratios. So this is just like a common one where it's 5 milligrams of oxy and then 325 of the acetaminophen. But, right, obviously, this could be found in different ratios, right? They make all sorts of combos, I'm sure. And then, so let's look at, so what would be an example of a heterogeneous mixture? And it doesn't have to be drug related, it can be kind of anything else. Yeah.
Italian salad dressing.
Yeah, that's always a good classic one. I like it. So salad dressing, specifically Italian, right? And you know, Italian, it's got, usually you have the oil and water mixture anyways, and then, right, all the nice Italian seasonings, peppers, all sorts of things in there. And so, right, that's the key, is that you can kind of see distinct little parts, right? Maybe you eat some Italian dressing or seasoning, right? That's kind of like a little more spicy. And so that's kind of the way I remember is, like, if the first bite and the last bite are different, or, right, you can kind of have different bites, then it's heterogeneous. And then obviously, again, same throughout, homogeneous. So what are other examples of, let's do heterogeneous mixtures? I mean, I would consider the atmosphere like more probably like homogeneous, unless you really wanted to get.
I mean, like up to the very.
Yeah, I mean, so that's where I say, right, like, what are we talking about? Because, like, usually when I think air, I'm just thinking of, like, the air that we breathe is, like, homogeneous, you know, 78% nitrogen. But, yeah, like, if you wanted to get technical, obviously, if we're looking at the entire atmosphere, then we have, like, thinner layers up above, so. Yeah, again, that's why I say, like, offer an explanation, right? So if you're thinking of the different layers and how they're different, like, I would write that on the exam, right? If other people in the room are just thinking about the air breathing, right, then explain that. I think it's the air in the room, and it'd be homogeneous since, right, we're all breathing the same air. I can't go stand in that corner and get more nitrogen or anything. So yeah, I'll probably put air under homogeneous, and then I'll honor your atmosphere. So again, kind of think of the total atmosphere, right, from our lower layers all the way to our stratosphere. Again, kind of more heterogeneous. Other examples, yeah.
Salt water?
So salt water, so is that heterogeneous or homogeneous?
Homogeneous?
Yeah, so salt water should be homogeneous. And again, this could be where you need to offer an explanation. So is it salt water that's completely dissolved throughout, right? Or did you just come from the Dead Sea? I don't know if you've seen the Dead Sea. I didn't think about this till now. But the Dead Sea, obviously, it's evaporating, so it's increasing in salinity. So maybe you just came from the Dead Sea, right? You scooped out a bunch of salt, and so then it would be heterogeneous, right? If you have like solid pieces of salt at the bottom, and then obviously some in solution.
Orange juice with like pulp that separates.
Yeah, so OJ with pulp, so that's a good one. And someone earlier had said cake, but I wanted to like clarify, because right, we don't want to just have like a homogeneous vanilla cake, but maybe, what's a good cake with stuff in it? Birthday with like sprinkles or something crazy.
Tiramisu.
Yeah, or I like tiramisu. That's a good one. So that one has pretty distinct layers, right? Tiramisu, you got the cookies, you got the whipped cream, and some chocolate layers. So yeah, that is very heterogeneous versus just kind of, right, a whole vanilla cake or whatever cake that is just, again, kind of uniform, right? So same thing with ice cream. So I like, you can just use vanilla ice cream for a homogeneous mixture. Again, kind of same throughout. And then chocolate cookie dough or something. Or chunky cookie dough ice cream for heterogeneous. All right, any other kind of examples that are burning that we're thinking of or on our mind? And so again, right, the whole point is to understand what am I working with, and then probably, right, how will I separate or purify it? So, and that's where we have, right, again, our pure substance. And generally, right, we want a pure substance, again, either an element or compound, and maybe you're trying to make a new compound. And then versus a mixture, right, which this could be a reaction mixture. And, again, that's really the hard part of chemistry is now you have a flask of stuff. How do you get it out? How do you purify it, right? How do you get it into a bottle, potentially? And again, we'll only touch upon purification, right? That's what your entire chemical career could be for, is purification. Okay, blah, blah, blah. So we have heterogeneous mixtures versus homogeneous mixtures. So we kind of went there. The only other thing I'll kind of add to this, we're not really on our catalyst chapter, but kind of thinking of where this would be used for, again, chemically. So I always think of catalysts with this, and especially, right, like your car catalyst, so catalytic converter. And so that's heterogeneous, right, since your catalyst is a solid metal, palladium, and then, right, your gasoline mixture is passed over. And so generally, this is, again, just like a very broad statement, but if we're talking about industry and thinking about trying to design something effective for industry, you usually want something that's heterogeneous, just because it's easier to separate, right, your catalyst and your product, versus some sort of homogeneous mixture, right, where they're all in the same phase for a reaction. So usually, if a chemist is talking about homogeneous mixture, right, it's a solution mixture, could be aqueous, could be organic, but, right, that's always the tricky part, is now once you have them all in the same phase and you do this wonderful reaction, how again, do you retrieve your product out? Or how do you retrieve your catalyst out if you can? So I'll just say issues with separation. So again, just broad things to kind of think about. And like I mentioned, there are many different ways to purify compounds. And so a simple distillation is one of the first techniques or common techniques here. And so that's kind of why it's included. I also like to point out the safety violation here. So I would never use an open flame to do distillation. This is how fires happen. So this illustration isn't very accurate, but usually, and we'll do a distillation, I think, second quarter if I remember, but there's a joint here, or there generally is, unless you were to have like a very specialized piece of glassware. But you have a joint there, and all that means is, right, liquid could escape from this joint. So if you're doing a distillation, right, you would never want to use an open flame, because if you get a little bit of flammable material leaking out of there, boom, your whole thing's on fire. So not a good thing. So no open flames. So use a heating mantle, which we have in labs. So again, you'll get to do this. And again, the idea is you separate two things with different boiling points. And then you can do a distillation. And then generally you use water to recool down the liquid. And then you can get your happy, pure liquid here, whatever it is. And then, yeah, the solid component is left. So you could do it very simply, right, separating out a liquid and a solid. You could also do two liquids as long as they're in different boiling points. All right, questions? And so let's kind of, again, we're kind of teasing the chemical and periodic table here. We're just kind of going towards it. And let's look at a few things. So this was determined pretty early, right? So again, early chemists and scientists are trying to quantify what's going on with a reaction. And so this was developed probably in the 1800s, this law of conservation of mass. And so in a chemical reaction, matter is neither just created nor destroyed, right? It's just converted from one form to the next. And so they did quantify this, right, at some point. So especially with combustion, right? So you burn something, and then it kind of looks like it disappears, right, since you're left with less mass. But then they quantified it, right, determined that actually you're losing that mass as water vapor. And so, yes, it is conserved, right? So that's, again, kind of what they were playing with. So, again, determining that they're just rearranging these atoms. So like I mentioned, there was a lot of confusion at the time since they didn't know what the gases were of oxygen versus, like I mentioned, CO and CO2. And so we can, let's at least appreciate the mass balancing concept here. And so that's what's being emphasized in this reaction. And I wouldn't advise ever trying to do this reaction. So you could take, right, sodium and chlorine gas and mix them, and I'm sure that'd be a very violent reaction, but then you would end up with nice table salt. And so it's saying we have 7.7 grams of sodium reacted with 11.9 grams of chlorine. Add those two together, right, for our total mass, and then we'd have 19.6 grams of salt. And again, right, they were kind of playing around with these proportions for a while. So Proust, I'm not quite sure how to pronounce that, but he made a few observations, again, just determining that they always form in certain ratios. Again, carbon and oxygen either went in this 1-to-1 or 1-to-2 ratio, which is how we got to this law of definite proportions. And so, right, basically, this is where they're starting to discover compounds at this point. So thinking back to our definition, right, define chemical formula. And they always kind of reacted in these, again, whole number ratios. And so also called law of constant composition. Again, right, we're just saying we identify this element and it's always going to have these proportions. All right, so let's kind of look at how that might have gone there. So we have, again, they were playing around a lot with carbon dioxide and trying to figure it out, what it was. And so they decomposed carbon dioxide into its elements. So one sample produced 25.6 grams of oxygen and 9.6 grams of carbon. And then the other sample produced 21.6 grams of oxygen and 8.10 grams of carbon. So try this out on your own, right? See if you could figure out what's the mass percentage, maybe calculate some ratios. So I'll give you a minute or two to kind of start that. All right, so let's kind of look at the two ways you could analyze this. So, right, first we could find our mass percent. So starting with our first sample, right, determine our total mass. So 25.6 plus 9.6. So 35.2 grams total. So that's what we started with. And then, you know, we could calculate either one. I'm just going to do percent of oxygen first. So percent oxygen, so let's see what that comes out to. So 25.6 divided by our total mass. And then, of course, multiplying by 100, keeping 3 sig figs, so about 72.7% oxygen. And then we want to see if our second sample is consistent. So again, we could repeat that. So sample 2, so same thing, let's figure out our total mass. So 21.6 plus 8.1. And so now we have 29.7 total. Take our oxygen again, so 21.6. And so, right, same percentage. So 72.7%. So again, right, we're seeing that they're always in this kind of ratio. So they haven't quite gotten to moles, right? You can kind of see that we don't have moles yet. So they're still getting there, but okay, just kind of seeing these defined ratios. You could also, of course, look at the two ratios instead of a percentage. So 9.6 over 25.6. Let's see what that is versus 8.1. So now I'm doing carbon to oxygen ratio to 21.6. So again, if we explore that as well, so we get 0.375 for their ratio for the first one. Let's see if that's repeated for the second one. So, right, exactly the same. So, okay, good. So again, right, all we've proven is that they're kind of in these same ratios. And a lot of other chemists kind of did work as well, like Pelletier also. I'll just add him in there. There's a bunch of people, again, at this time. He was doing really similar experiments, so a lot of like tin and copper, trying to make those oxides. Again, just kind of proving the same thing, that they're always just in these same ratios. Okay, but still haven't quite gotten to atoms there. And so then 1804, then we kind of start at least getting closer to the idea of atoms with Dalton. And so right now we have kind of the law of multiple proportions. And so now he's saying, right, we have elements A and B, and they can form different compounds. So again, this is kind of related to this CO2 work, right? Because he found, well, not only can CO be in this, well, again, looking back, right, we can tell it's a 1-to-1 mole ratio. At the time, they're just looking at mass to mass. Or they can be in this, right, 1-to-2 ratio. And it's always kind of this ratio of small whole numbers. All right, so again, right, we're teasing our defined chemical formula. It's always kind of awkward too, right? Like looking back at history with what we know now, it's like, yeah, we know it's all atoms and everything, but at the time, right, it was still difficult to understand, right? They didn't know oxygen was diatomic, so I'm not sure when they figured that one out. So all these difficulties. And so again, right, they played with carbon dioxide and carbon monoxide, and of course found that it either reacts in this nice 1-to-2 ratio, or 1 to 2.67 grams, or this 1 gram to 1.33 grams. And again, it's just in grams, since we haven't quite defined what a mole is historically. And so again, right, we get a small whole number ratio, which is essentially our formula. All right, so now looking at what our elements are made out of. So looking at our subatomic particles. So this is a good kind of cheat sheet here. So we have, right, our proton and our neutron. So of course these comprise the main mass of our atom. And so do we know how we found the nucleus? All right, so the nucleus, so that one is a good experiment. So again, right, it took a while to tease out all these parts. First, it kind of started with, right, what is the nucleus, or really what does the atom look like, right? So kind of, you have Dalton as just kind of this undefined blob, and then at some point you got the plum pudding model. So the plum pudding was just basically, they surmised that there were protons and electrons and other things, but everything was just kind of distributed around, right? Like a pudding, you know, you have a pudding and imagine just throwing like blueberries or something in there. But then, so this was disproved, yeah, now I'm blanking on who, oh, Rutherford, sorry. So Rutherford, he set out to find the nucleus, or rather he was trying to prove or disprove this plum pudding model. And so what he did is he bombarded a sheet, oh, I didn't mean to put a line there. He bombarded a thin sheet of gold foil here with alpha particles. And so the idea is, right, if we have this plum pudding, it should run into the components and then kind of be scattered, right? This alpha particle will be scattered onto the detector. And so what actually happened and why this was so amazing is, so okay, they shot these alpha particles and then found that most of them pass straight through the atom, right? So they're all just passing through unperturbed. And then sometimes, though, they would shoot almost directly back at them, right? So then what that told Rutherford is that we don't have this plum pudding model, but rather, right, the atom is mainly empty space. And then we have a center, right, our center nucleus, where all our mass is found. So kind of going back to our cheat sheet, oh, so let me just put, right, we have our proton and neutron in the center of our nucleus. And so going back to this little guide here, so it tells us, and we have the mass in both kilograms. And then notice we have this atomic mass unit. We'll go into where this exactly is derived from in a second. But basically we have protons is 1.67 times 10 to the negative 27 kilograms, or 1 AMU. Same thing with the neutron, right? They're both considered about 1 AMU. So you can add them up to find our total atomic mass of one isotope. So again, we'll get into that, kind of introducing different terms. Notice your neutron does not have a charge. So the neutron itself, I think it was a while before they teased out that the proton and the neutron were separate, right? So again, going back to Rutherford, they just found that most of the density was in the center, and then later had to tease out that, yeah, the neutron was in there. And then the electron, so this was discovered, well, I should say J.J. Thomson was the one that, that kind of quantified this electron and got the mass of it, so he was able to do this, not Thomson, Millikan oil drop experiment, sorry. Millikan's oil drop experiment. And so he was able to get the charge of an electron, so he had this little piece of oil and then was able to stop it in an electrical field, and so that's how we get the charge of an electron. And so notice, right, the proton and the electron are opposite charges, and so eventually we'll quantify this charge, but what we need to know is the proton is +1, then electron is formally -1, right? So that's just our convention. And then we consider the mass of the electron to be 0, so you can see it's right 0.00055 AMU. So again, we don't count the electron when we add up our mass of our isotope. And so kind of where we're headed is, yes, we have molecules, and right, our elements can combine to kind of form molecules. So just showing you some, right, hydrogen chloride, water here, ammonia, methanol, but again, we'll kind of get to this as we progress. All right, so let's look at kind of naming. And so let's start with ionic compounds. Well, let's back it up for a second. What is an ionic compound? So now we're getting into how things are found. So does anybody know what an ionic compound is? What's the easiest definition? Yeah.
I don't remember the exact terminology, but it's basically where one, you have ions of elements. One is a positively charged ion, one is a negatively charged, and if I recall correctly, they share a valence electron.
So they don't share, but they transfer electrons. But let's back up and we'll go even more simply, right? So an ionic compound is what happens when we have a metal plus a nonmetal. And so now let's look at our periodic table. So periodic table, right? Most things are a metal. So right, looking to the left of our staircase, I would put, so right, mainly we're going to look at groups 1 and 2. So those are the easier ones. We'll look at, so all the transition metals, we'll look at why they have funny naming systems. And then we'll talk about like aluminum and gallium because those get special. We'll look at why. But right, so again, basically any of our metals combining with our non-metals right over here on the right. So going on the right of our stair step here. So right, sodium chloride is obviously an ionic compound. Potassium oxide, right? So we could come up with all sorts of different formulas. And so I also want to add in there, so again, we'll kind of get there. Your book tackles naming first, so that's why we kind of shove it here. But what's going on is, right, we have our metal. And so metals always tend to lose electrons, right? So metals are always looking to donate electrons, so we'll look at that with kind of the reactivity. But you can appreciate that with the oxidation states that you've been given. Oops. So if you have, right, your periodic table, and you can also probably see this on other periodic tables. So this is starting to get into these little oxidation states, they're called. So right, your periodic table has this nice guide there. And so that's just saying how many electrons, right, it tends to give up. And so if it tends to have a positive oxidation state, then that's saying, right, it tends to lose metals. And then this would become what's called a cation. You can remember because it's positive. And then it's paired with our non-metal, which is going to gain that electron, right, that the metal has donated. And so you can tell, so what's kind of confusing about this periodic table is it lists like the most common one on the bottom for some reason. And so it's fine, you know, with fluorine, that's easy to understand, but then chlorine, you want to just focus on the negative one, so that's the most common oxidation states. And then all those other positive oxidation states are more like formalities when we do electron counting with covalent compounds. So we'll come back to that, right? So mainly you see, and we can write it. Let me see, do I have a periodic table? I forgot a periodic table. Let's get a table. Sure, I have one somewhere. Oh, geez. Let me copy my own notes. Sorry. I got a periodic table somewhere. There it is. Let me move it to my other notes here. So again, right, starting to get into our oxidation states. So just kind of brief overview. So our halogens, right, they tend to have a -1 oxidation state, meaning that they accept 1 electron. Oxygen, -2. So accept 1 electron. right, gain 2 electron typically. And then -3, at least for nitrogen and phosphorus. Okay. So that's starting to kind of come together. And this nonmetal becomes our anion. All right, so then we're given, right, this little distinction. So it says metal forms only one type of ion versus a metal that forms more than one type of ion. Well, what this is referring to, right, is mainly our groups 1 and 2. And again, right, we can kind of see why. And I feel like we're going to get a little, like, again, kind of bear with me, right? We're all trying to get on the same page. And so there's kind of a lot to kind of get on board with, but we can see that. So again, we're starting to understand the reactivities. So, right, lithium, sodium, potassium, they all give up that 1 electron. And they will always only give up 1 electron, right? We'll really delve into it, but we're starting to see that. Same thing with this group 2, right? It's always going to lose 2 electrons. We're going to see that in its reactivity. So that's our first type, right? So basically we're saying we always know the oxidation state, right? So lithium, when it's in a compound, it's always going to be +1. And then there are a few others that are also considered always to be the same. And so that's going to be zinc and aluminum for the purposes of our class, and then also silver for the purposes of our class. I don't like, this kind of bothers me because there is like silver 2+ and other things, but again, for our class, for Gen Chem purposes, it's always assumed to be 1+. So like I mentioned, right, chemists are always kind of trying to do funky things. So that's one of the few exceptions, but otherwise, yeah, zinc, aluminum, those are always going to be the same. So zinc's always 2+, aluminum's always 3+. So everybody's still with me so far? Makes sense? All right, so then how to name these is, I think, a lot easier. And so we just say the name of our metal cation. And then we add our base, we just change the ending to "ide." So then we have, right, potassium chloride, calcium oxide. And so this starts to get into other things as well. So right now we're just going from like formula to name, but I do want to point out that our charges are balanced. So I'll point that out now. It's going to keep coming up, right? Again, just kind of, I want to make sure we're all on the same page. And you can see that, again, I'll look at our periodic table for a second. Let's flip to this one. So potassium chloride, so 1-to-1 ratio. We know they're 1-to-1 since potassium, right, is in their first column, 1+, and then chloride, -1, so yeah, it's going to accept that 1 electron. And then same thing, right, calcium oxide. So calcium, if we go back to our periodic table, now it's in group 2, so 2+, right, so it's donating 2 electrons. And then they paired it with oxygen, so again, oxygen accepts 2. So again, 1-to-1 ratio. So calcium 2+, oxygen 2-. So they balance out, right? And so there's no physical sharing, no bond between them. So they're just kind of repeating units. So I should have. That's a wonderful thing about the internet is you can just look something up so you can appreciate it. So right, they are in this repeating unit. So this is a crystal lattice structure. I'm sure we'll look into this a little more in the class. But again, right, repeating units. So I believe the potassium is purple, chlorine is in green. They're not quite to size there, yeah.
You said there was no bond between them, but those are ionic bonds, right?
Yeah, so it is called an ionic bond, but again, there's no like physical sharing. So it's just the electrostatic forces that are keeping them into place, right? So that's why I wanted to show this structure here. So it's again distinct. So let's look at water again, like not to be water, and this is a covalent compound, right? And it's, you can tell by how it's drawn, but it's implying that, all right, they're sharing these electrons. So if we go back to this one, so again, crystal lattice structure. So it's just the electrostatic interactions, right? Something positive, negative, so opposites attract, and then they're all repeated around, so of course depending on the crystal structure. And so that's what makes it incredibly strong, right? But then we can start to get into the other properties of these ionic compounds, right? So ionic compounds, and I might be going off on like another lecture, but this is fine, this is the beginning. So ionic compounds, they tend to be really brittle. So, right, just think of salt, right? You can't really just like cut salt, and if you do, it like shatters, right? It's very, very crystalline, right? So brittle, and then they usually have extremely high melting points, and so they shatter. But again, all that goes back to its structure here. So this crystal lattice structure, so you can try to think of putting a knife to that, right? And trying to separate all these things that are held together by electrostatic forces. And yeah, so when you do separate it with the knife, right, they tend to kind of shatter and break off. All right, so back to naming. Sorry, before I get too excited. So I'll write some other compounds and you can write out the name. So magnesium fluoride. Let's do lithium nitride. Oh, maybe I wanted to go the other way. And we'll try that one. All right, try those three there. See how you do. Again, I probably should have gone the other way, but and if you're in the chat, you can write your answers in the chat. So what do we think for magnesium fluoride? Again, I should have gone the other way, but what do we think would be the formula now? What do we say? So look again. So what's our oxidation state of magnesium? Positive what? So positive 2, and then what does fluoride tend to be? So negative 1. So then how many fluorides do we need to balance this magnesium? 2. So excellent. MgF2. So thanks for following, even though, like I said, I probably should have given you MgF2. And then what about lithium nitride? So I wanted to show you nitride because for some reason everyone always gets confused So what is nitride?
NO2?
So not NO2. So remember, it's just "ide" here. Yeah, so it's just nitrogen, right? So again, that's why I brought it up, because for some reason it confuses people. And so nitrogen, right, again, it tends to accept 3 electrons. So then how many lithiums would we have? So 3 lithium nitride. And why don't we look at that? So this is a fun chemical. And I like to bring it up only because it's kind of funny, and it's blue. I'm trying to get a better picture of it. But basically, so right, most things do not react with nitrogen. So I don't know if you're aware of that. So basically, right, they have these whole things. Now I'm really going down the rabbit hole. But you can have what's called a glove box. And so it basically looks something like this. Maybe you've seen it at, like, sometimes museums have it for like space rocks or other things they want to keep away from oxygen. So that's what it's for, is providing an inert atmosphere. So generally nitrogen is used if you're rich, maybe argon, but I've hardly ever seen argon used. And so I just bring this up because lithium can react with nitrogen, and so your lithium metal in your glove box starts turning this like nice bluish color. It doesn't really affect the reactivity too much, but it's just kind of interesting because, like I said, most things don't react with nitrogen. I was trying to find a better picture. Darn. Yeah, unfortunately the Wikipedia page was the best kind of picture, because it is this, like, they call it reddish pink, but to me it looks kind of more like a blue sheen on it. All right, and then the last one, so how would we name Na2S?
Sodium sulfide.
Sodium sulfide. Excellent. All right, let's take our break now. And so let's come back around like 12, 10-ish roughly. Then we'll continue naming. The homework can be separate. Yeah, that's fine. Like, sorry, what are you asking? Like, do you want me to print them, or are you trying to print it?
If there's a way to print
so the notes should be like sharing.
Yeah.
So then you, there should maybe be a way to print them from your side. Is that what you're asking?
Yeah.
Yeah.
I just didn't see like a little box because it's a different. I didn't know if you would know where I was.
I mean, I could look at your.
I haven't touched this since we went to the lab. Don't even until Thursday, so. Last night I thought I forgot to turn my emails in, and I think the due date is today. I was like, I was going to make like email my stuff. Oh yeah. It's due tonight. So. We're gonna be here about for the first week of the staff. Yeah, I know. All the homework and stuff was due for this class today. So I was doing it last night. I know, it's last night. Yeah. And I was like, I just should get it out. It's mostly using answer key. It was stuff that like we're going over today, so. real though. So I'm gonna go back here.
No.
And I had to buy my textbook.
Can you print this?
Oh, yeah.
Yeah, I don't know if you could try to like email it yourself.
Yeah.
Yeah. I might eventually try to post a PDF, because that's what I used to do, is just I was trying to update my notes, and then I was fighting with OneNote.
How you doing?
Good, how are you?
I had sent an email. I had trouble getting through the firewall in the Journal of Chemistry. And I was wondering if there's like, do the computer lab computers, they just bypass that?
It should, but
Yeah.
yeah, if you email it me again, I can like send you the article directly, since
Yeah.
Otherwise we could look at it after class, or
Yeah, I just
maybe
wanna be
like
able to
right
get it
now.
into the lab for
Do you have
you
your
today.
computer right now?
Yeah, I do.
We could look at it.
I didn't realize I had to create an account. That was my whole thing. I just had to make
What
an
do you
account.
want?
Oh, is
And
that
then I
right?
could access it.
It wasn't just your student ID and password, that was like what I got caught up on.
Yeah, no, I
on
had to
their
just
help
create a
questions.
new account and then
Really?
it worked fine.
Okay. Well, I guess we'll try that. We'll see. So you ran into that same problem?
Yeah, I couldn't get onto it. I couldn't find things to do. I didn't know what was going on.
Maybe I'll get the info from you on where you create the account if I can't figure that out. Well, if it doesn't work, I'll submit it that way.
Yeah, I mean,
Yep.
it's okay if it is late.
Thanks.
We're trying to figure out how to get on there.
Oh, and it had a pop-up that said pair, but I didn't read it first, and hit pair with your institute when it does come up. So,
Yeah,
so I missed that the first
I tried to
time.
do that.
Okay.
I did that.
Password right now. I need to double check if I'm on the.
Oh.
Well, obviously right now.
Could I ask you a
Listen, I'll
question
see if
about the
I can
text?
show you, but,
I'm just kind of curious how they're like structured, like you give a study guide and how that goes.
Don't give a study guide. We usually do a review on Tuesday.
Okay.
And yeah, I don't know what your exam's gonna look like yet.
Okay, do I need a Scantron or?
No, you don't need a Scantron.
Okay, review's nice, I like that.
Just that. Should be. Yeah, but it says. Go back to what it was. First 20 characters.
Yeah? So I did it with her in class, but if you go to the RCC site and then you go to library sources, blah, blah, I'm trying to remember if they found it. Yeah, it is this, and then I created a new account here. I did, download the article. So if you would keep it. Oh. Yeah, I had to create a new account, and then I exited out of this at first, I was like, I hate pop-ups, and then I was like, oh, I was supposed to click on that.
Alright, do we all make it back from break? Anybody fall in?
Anybody not here, right?
Yeah. Anybody not here?
Raise your hand.
Oh, there we go. Some more stragglers. All right, so let's kind of continue. And so again, I apologize if it feels kind of scrambly, right? Again, we're all just trying to get on the same page and trying to figure out how to discuss chemistry. And so I kind of respected how your book treated it, right? And so your book was kind of like, here's how we at least name simple things. And so again, that's kind of why we're like jumping, or like it may feel that we're jumping around. Like I said, it improves chemistry once we kind of get past the language, right? We're just trying to get with the same language, how to communicate properly. And so your book switches to molecular compounds then, and it focuses on binary molecular compounds, right? So just meaning our very simple covalent compounds in a sense. And again, by molecular compounds, I would also use the term covalent, which means now we're referring to things that are sharing electrons. And so kind of the problem with these covalent compounds, right, is it's different from our nice ionic compounds. So again, our ionic compounds, we can predict their ratios from these oxidation states. But you can probably already guess the trouble with these molecular formulas, right? It starts with CO or CO2, right? The fact that these are both covalent compounds. So how do you name carbon and oxygen? And so this is what all these little prefixes are used for. And we'll look at kind of naming hydrates as well. But let's say we have, so looking at CO, so we'll start with CO. And so notice, unless you have multiple elements of the first one, so we'll look at two examples at the same time. So N2O3. And so if you have multiples of your first element, you would use a prefix, but you don't generally say like mono. So right, like carbon monoxide, we don't say monocarbon monoxide. But looking at this N2O3 one, well, we need to say dinitrogen since there are two nitrogens in that one. And so this one I'll just say carbon. And then again, right, we need our prefixes to indicate how many of our second element. And then we change our ending to "ide" again. And again, write down these prefixes if you're unfamiliar with them. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And then, right, you could go on and on and on if you had other crazy compounds. And so then CO becomes carbon monoxide. And so this one is dinitrogen trioxide. So there's that. So I'll put up a few and then you can practice that. So let's try, we'll do our variations of NO. Try that one. So yes, try those three there. So what do we get for the name of NO here?
Nitrogen oxide?
So nitrogen, but then what do we need to add to the oxide here? Monoxide, excellent. And what about N2O? So dinitrogen monoxide. And then what about this last one here? Tetraphosphorus decaoxide. Excellent. All right, so those again, relatively straightforward and very specific use case. Yeah.
I think I remember reading in the book that the mono was dropped except for when with carbon and nitrogen. Do you want to strike mono if it's just mono?
So if it's in the front, then it's drop. Yeah. So if there's only one of that element, like this one, right? You don't say mono nitrogen monoxide.
Okay, maybe I read it wrong. I thought
Yeah.
it was talking about for the second word that mono wasn't usually used except for carbon monoxide and sometimes nitrogen monoxide.
Yeah, I would check that because yeah, usually you always have the monoxide or yeah, if you have a specific like compound example in mind, but yeah, it's definitely always monoxide. But like I said, if it's only one on the first one, that's when you omit it. And I mean, again, very specific case, right? Because usually your molecular compound has more than two distinct elements, but we won't go into organic naming. So that's what organic chemistry is for. And then again, other things, so we're kind of all on the same page, and now we want to look at our formula mass or molecular mass of a compound, right? So formula kind of referring to more of an ionic compound and molecular with a discrete compound. And so this is just our mass of our formula unit. We could also be talking about, so we'll look at what this means, right? We can either talk about the mass of an individual atom or molecule, or we can scale it up to 1 mole. And so now let's look at where this comes from. So if we look at our periodic table, and so we can, let's just look at carbon for a second. And so we have, sorry, let's back it up. Let's back it up even more. So this is kind of, right, our average. So there's a couple of things that we need to understand. So first of all, right, this mass on the periodic table is the average of all our isotopes, right? So we have to understand that. So this mass that we're getting is, again, just kind of an averaged mass. So from periodic table, so right, I'm just looking at carbon, and so its mass, right, is 12.011, and again, average of isotopes. So, and this could be atomic mass units, again, if we're talking about 1 carbon, and that's the average, or if we're talking about, right, 1 mole of carbon is 12.01 grams per mole. And so, right, simply that's all that is kind of saying, right, is that we want to just add up our compound mass from our periodic table. And so again, just looking at this, so we have water, so 1 AMU of hydrogen, and then there's 2 of them, right? So you can see in our formula, water has 2 hydrogens, multiply it by the appropriate amount, plus 16 for the mass of oxygen. So let's calculate another one. Let's try, let's try PCl3 for a second, or phosphorus trichloride, right? So see if you can add up, again, just from our periodic table.
Is that healthy?
So yeah, it's PCl3, but Cl, right, is chlorine. All right, so what do we get for our mass of PCl3 here? And so, right, you may have some discrepancies in your answer. I'm not too picky on rounding, right? It depends what your periodic table reports it to and then how many sig figs you use. So I have 30.974 and then plus 3 times 35.45 or something like that. And so what do we get for our mass? Roughly, what do we get? So 137 point what?
324.
324. And again, right, we could be talking about grams per mole if it's a mole of it, right? So this would constitute a mole. We still need to define what a mole is, but that's kind of coming. Or we could be talking, again, about the average of an individual one. So this is still, right, just an average. So let's kind of look at some other things. So is this clear how to calculate the mass, by the way? All right, so I want to move on to back to this 12 grams and kind of pesky things that we need to look at. And so like I mentioned, this is an average mass, right, of our isotopes. So going back to carbon, so it has 12.011 as, again, this kind of average. So this is our average atomic mass. And so, well, where does this atomic mass come from? So what do we know? Do we know about isotopes? Have we heard about isotopes before? Yeah.
Are they the ones that have like extra, is it neutrons?
Yeah, neutrons. And so, yeah, it could be extra, could be deficient, but yeah, essentially, basically different numbers of neutrons. So excellent. So let's write that. So isotopes. So elements with different numbers of neutrons. And okay, so let's again break this down a little further. And so we had said that our proton, right, that gives us the identity of our element. And so let's start with carbon 12 again so we can understand where we're at. So carbon 12, so 12 stands for our total mass, and if you're ever lost, right, you can always go back to the periodic table. Always a good place to go. Okay, carbon, yes, it has this number 6, right? So 6, again, giving us our number of protons. And so it always has 6 protons. And then we should remind ourselves that the total mass of an isotope, right? And this means that we're looking at one individual isotope, and that is equal to the number of protons plus the number of neutrons. And again, right from what we had said, the electrons are negligible, so we don't need to include that in our mass. So that means, right, carbon-12 then has 6 protons and 6 neutrons. Oops. And so what does that mean then for carbon-13? So how many protons does it have? 6 protons. And then how many neutrons?
7.
Excellent. So right, it's heavier. And so then kind of a fun fact. So carbon-13 is about 1% abundance. And so this is going to get back to right our average mass. And then does anybody know the other isotope of carbon? Yeah, carbon-14. And do you happen to know what's special about carbon-14?
I think I remember from biology class, something, it reacts with sunlight, it's absorbed into living things, and then use it for carbon dating.
Yeah, so it is, I don't know about the sunlight, but yeah, it is incorporated right into your living organism. So, right, any living organism is obviously eating carbon and incorporates it, and then, yeah, when that organism dies or yourself dies, then you can do radioactive dating, kind of comparing these isotope ratios. The abundance, though, of carbon-14 is incredibly tiny. So it's 1.2 parts per trillion percentage, or 1.2 times 10 to the 14, or sorry, negative 12. So extremely tiny. So I'll kind of ignore carbon-14 for now. We can at least say it has 6 protons and then how many? 8 neutrons. Excellent. And then so carbon-14, like I mentioned, is radioactive. And so this is something that scientists don't quite understand exactly, but just what you kind of notice is as this like ratio gets kind of more off, I mean, obviously as we get heavier into the heavier elements, the ratio can really get off and it's okay. But especially on these lighter ones, for some reason, right, this is unstable, carbon-14, and so it undergoes, right, radioactive decay. And so you just kind of see that, again, right, with certain isotopes as they become, I would say, off balance or so. But again, difficult to predict these trends, right? Scientists don't fully understand why certain compounds are stable, why some are radioactive, but again, that's what we observe. All right, so back to, well, how the heck did we get 12.011 on our periodic table? And so this is, again, if we were to take the average of all our carbon atoms. And so basically, if we could have all our carbon atoms step on a scale, if we had 100 of them, right, 99 of them would have a mass of 12, and then that last 100 would have a mass of 13, right? And so if we kind of just do some rough math, right, we could do, okay, 12 AMU times the abundance, so 99, or 0.99, so converting percent to a decimal, plus 13 times 0.01, right, for 1%. And so I'm just adding, again, right, the mass by its percent abundance. And again, I'm doing probably kind of quick and dirty calculations, so it'll be a little off. Obviously, whoever did this took much more careful measurements, much more precise in their abundance. But, right, that does give us roughly 12.01, so that rounds. Again, that's our average. We can kind of see this more clearly. I always like pointing out bromine. So bromine's always fun to look at. So we have bromine here, atomic number 35, and then it has this average mass of 79.9. So there is no isotope of bromine that's 80. So bromine is fun because it has 2 isotopes, and only 2. And they're about a 50% abundance each, or 1-to-1 ratio. And so you have bromine 79 and bromine 81. And this is super nice because it's really easy to identify a bromine compound. And so now, kind of gone off. It's a rabbit hole here. So kind of trying to look at other things and understand how chemists do things. So we have a technique called mass spectrometry, which of course allows us to get the mass of ions. And so basically you have this source that can ionize your compound. So depending on the mode, it can make it positive or negative, and then you detect it. And what I want to show you is why bromine is so fun. And again, you can appreciate the isotopes. So bromine, oh, that's not the one. I wanted something a little easier to look at. Oh, come on. So this is Br2. And so you can tell, I was trying to find one with 1 bromine. Maybe I'll have to search around. But bromine, so you can tell that it makes this nice distinct pattern if there's 2 of them. So now you have to do math. But basically, right, if you have 1 bromine, it shows up in the mass spec as these 2 lines that are 2 mass units apart. And then if you were to do, so now, I don't know, a small bit of game theory. So, right, if we have 2 bromines, if now you have 2 bromines, right, basically what it's saying, you have different permutations, so they could be 79, 79, they could be 81, 81, or 79, 81, 81, 79, right, which gives us that distinct triplet pattern. Sorry, that got overly complicated. But again, very distinct isotopic pattern, so then you can tell, oh, okay, that's bromine. Or, you know, in this case, right, that's chlorine here. And this one is like this 3-to-1 ratio based, again, off of their abundances. So you can see here, chlorine 35 is 75%. Chlorine 37 is about 25%. So again, distinct isotopic patterns, so that would help you identify compounds. And so then other things that you might need kind of for your homework, again, we're just trying to all land up on the same page, is so we have isotopes. So does that make sense for isotopes? What they are? Kind of how to find them. So again, right, your protons, you always go back to the periodic table, and then you may have a mass. But now let's look at ions. So again, we had kind of barely talked about them. And so let's look at like what could be on your homework. Oh. Let's look at, so let's do strontium. We have strontium 90 here, and I'll put a 2+ charge on it. And so we want to figure out protons, neutrons, and electrons. And so we can look up strontium. So how many protons does strontium 90 have? Again, 90 referring to its mass for this isotope. So then what would the protons be? So 38, right? Go back to the periodic table, and I'll show it again just to be explicit. So strontium, right, group 2. So find it on your periodic table if you're not familiar. 38, okay, again, that's our number of protons. Excellent. So then, what's our number of neutrons? What do I have to do mathematically?
52.
So 52, or right, 90 minus 38. So then we have 52 neutrons. And then, right, just appreciate it how the numbers just start getting more and more off for, again, whatever reason. That goes into more philosophical discussions over why things are in certain ratios and abundances. But anyways. And then how many electrons do we have?
36.
So somebody said 36, so excellent. And if you didn't see that right away, so let's, again, kind of look at different ways to figure it out. So the way I like to think about it is I say our charge is equal to, right, our number of protons. And I always add them, again, in my brain, so plus electrons. But that's because, right, electrons are negatively charged. So maybe you need to do protons minus electrons, or think about adding, right, a negative number. Does that make sense? And so what we're really trying to say is that if it's neutral, or that means a charge of 0, right, that our protons and electrons are equal. And then in this case, so again, kind of depending on your brain and how you want to approach this. So if you have a 2 plus here, some people just subtract, right, the number of protons here to give me electrons, and then maybe you just re-add it for sanity check. So 38 minus 36, or plus my negative electrons, so that gives us back to positive 2. So let's try another one. So let's try 127 iodine here with a -1 charge. So give me protons, neutrons, electrons for that one. Oh, sorry. So then what do we get for protons for iodine?
53.
So 53. Excellent. So again, right, just read that from the periodic table. So let's find, there it is, 53 iodine. And then I made up an isotope, so 127. So then what's our neutrons?
69.
So 69, so 127 minus 53. So what do we say?
I do, my bad.
Oh.
122 instead. So it's 74.
So 74, sorry. So always good to double check our math here. And then how many electrons, right? So now we have a negative charge, so we have more electrons than protons is another way to think about that. So 54, so right, you could look at the protons, see, okay, well, I need extra electrons, so I'm going to add 1 to that, so 54 electrons. You can also do, right, algebra up here, so kind of whatever feels good. Oops, questions, sorry, I keep. So let's maybe start well, I don't want to rush anything. All right, do we feel okay with isotopes? I'm debating like whether we should continue with chapter 3 or whether I should talk about more things with isotopes. Maybe we'll just look at chemical changes and kind of start looking at our periodic table, unless I skipped anything on the homework. Again, this isn't really a criticism of your book. It's just the nature of chemistry. It's kind of hodgepodgey in the beginning, I always feel. All right, so I'll post chapter 3 notes shortly. We won't get too far. But again, right, we want to think about what we're doing in this class. So of course, we're going to be looking at chemical reactions and describing them. So we have to be able to write them and understand, well, what is even a chemical change? And so of course, a chemical change is something that alters our composition. But again, I'll highlight that it's really just a rearrangement of our atoms. So again, going back to all our conservation of matter principles and law of definite proportions. And I always like this little schematic here. So we have our iron. So again, it's just a metal here. So repeating iron units, and then eventually it gets compromised by oxygen. And of course, you've seen that if you leave a nail out. And then again, appreciate how it starts making this new structure. So here's iron oxide. And so again, these things would have to be determined by a crystal structure. So then that gives us, right, a true accurate picture of what our molecule looks like, which is also pretty powerful. And then I'd kind of skipped this multivariable naming just because your book skipped it, but maybe we could at least look at it really quickly. Again, I'm not trying to jump around, but maybe it is at least relevant to explain how to name it. And so if we go back to our ionic compounds, we have this like metal that forms more than one type of ion. And so that's referring to mainly, right, our transition metals. So it's down here, transition metals. And we'll get into, right, these other exceptions later. But just a kind of quick rundown of it is that we need to specify our charge. And so kind of going back to this example here, just again so we're all on the same page. This Roman numeral here refers to its oxidation state. And so if you look at your periodic table, right, you can see iron, and this is not limited, right? So iron can be in the 1+ state. I don't really see iron 4, but maybe. But we have iron, definitely iron 2, definitely iron 3, maybe some iron 6. And so to specify, again, what oxidation state it's in, that's what the Roman numeral is for. So again, we'll come back to this and kind of do more practice. But I at least want to show that. And so this is kind of the newer style of naming. So again, we'll look at that probably a little later. And then again, kind of balancing our charges is the thought here. And so then kind of looking at what our homework involves this week is we're just kind of going to be practicing writing these chemical equations. And so like we mentioned, right, it involves this rearrangement of our molecules. And so the key point is that we want to have the same number of atoms on both sides. And so looking at this statement here, so we're looking at a combustion reaction. And let's look at a few other things as well. So again, there's a lot of packed information in this chemical equation. So if you were in grad school, right, doing a brand new reaction or trying to make something new, you'd want to have your reaction, right, prominent on your top of your page. So this is what you're doing. And then let's appreciate all the information that's packed in here. So obviously, right, your exercise is, again, just to make sure that we have the same number of atoms. So carbon and carbon, so 1 carbon, right, 4 hydrogens, 2 times 2, so 4 total there. 2 times 2, so 4 oxygens, and then we have, right, 2, and then distribute this 2. So notice how your coefficients are distributed. So, right, we have 4 oxygens. Okay, so that's just kind of the first basic thing that you'll want to do. But then notice what else is included, right? We also want to add their physical states. So this starts giving us clues over how we're actually going to perform the reaction, right? What state is it in? Is it going to be, so, right, obviously this is a gaseous reaction, maybe similar to our balloon demo that we did. So 2 reactants in the gas phase. We expect to make, right, a gas, and then we might make a liquid, or, depending, again, on how exothermic that process is, we might just make water as a gas as well. So that's our states, and usually, right, the state will kind of be their standard state at room temperature there. And then there could be other information as well. So that will be like coming down the line, but kind of in the middle here, that's where you add conditions, right? Do you add heat, maybe UV light, anything else, a time, other instructions could sometimes be there. All right, we'll stop there. So we'll continue with stoichiometry. Let me know if there's anything that we kind of missed in chapter 2. I think I hit it all with the ions and the isotopes, but if there are questions or anything that needs clarity, especially on the homework, let me know so we can clarify that. But like I said, we're going to look at stoichiometry and then go back to our periodic trends and really understanding.
Why did they take all the station states out?
They're just somewhere else.
Oh, okay.
It's just like how the book was written. It like wants you to focus on like simple compounds first and like how to write it. But yeah, it didn't like go into oxidation states and all that.
I thought it was complex when we did 104, but I think we can handle it.
Yeah, like I said, it's coming down the line. It's just like it's a little scrambled.
So I completely forgot to press send the email I wrote. Is there any openings on Thursday for the lab?
On Thursday.
Because Tuesdays when we do tests in math, and I can miss Thursday.
Okay. Yeah, I think we should be able to squeeze you in on Thursday.
Okay, and I couldn't do it online because technically I was class in that slot, so it won't let me do it on my phone or computer. I'll do it here.
Okay, so yeah, shoot me another email then, and then I can get you in the class.
Okay, thank you.
Are you still doing quizzes every Thursdays?
Yeah.
Okay, so I know they're just going to be on like the chapters that we went over. So
Yeah,
you guys will read chapter 1 and 2.
Yeah, so it'll
Okay.
be like converting stuff like that, easy stuff.
Are they like short quizzes or?
Yeah, it's like 10 questions.
Okay.
Yeah.
Specific place to help find.
Those should be posted with like the chapter 1 notes if you go back and look at them. I think it's on the last section because I did it during recitation.
Oh,
so then it should be there to check. And then if it's not, you can...
And then do we need to memorize these?
No. So yeah, I haven't quite gotten that far of what the exam's going to look like. But at the very least, you'll be allowed to use that. Or if I don't let you use that, like the prefixes would probably be provided as like a cheat sheet.
Okay.
So I wouldn't make you memorize the prefixes. But I think my inclination is to let y'all use that on the exam.
Okay. Thank you.
All right, and then I'm going to stop this stream unless there's any burning questions. Speak now or forever hold your questions.
I went to a different class and I took the whole class on accident. Is it what we saw today on Blackboard?
Yeah.